Baking powder has been used by generations to remove undesirable odors from refrigerators, and various powders are used routinely on smelly sneakers in hopes of accomplishing the same. If your water source contains a high amount of sulfur or phosphorus, then you more than likely appreciate the value of an activated carbon water filter. So you might ask, what do all these scenarios have in common? Well, it turns out that in each of these purification processes, there's an adsorption process in action that, of course, has its roots in material science. Hi, my name is Ken Milam. I'm an application engineer here at Thermopore. Welcome to Thermo TV. In this series, we'll be discussing absorptive or chemisorptive filtration, also referred to as gas phase filtration, when the filtration is specific to contaminants that are in a gas phase. Our discussion will involve three parts. First, we'll discuss the filtration mechanism that enables the capture of these oftentimes molecular-sized particles. Then we'll discuss Thermopore's polymesh chemisorptive filtration media and how it's been designed to excel in these challenging applications. Lastly, we'll round out our discussion by comparing polymesh chemisorptive filtration media to several other similar yet different technologies that are also available on the market today. Okay, so let's get started. I think it's first appropriate to differentiate two types of chemisorptive filtration from one another: adsorptive from absorptive filtration. Adsorptive, spelled with an AD, is the addition or the accumulation of molecules on the surface of a material. This process creates a film of the adsorbate, the molecules being accumulated on the adsorbent's surface. Now, this is the basis for our discussion today, so let me say it again. Adsorption is the addition of adsorbate particles onto the surface of an adsorbent material. Now, adsorption is different from absorption, spelled with an AB. Absorption involves the diffusion of one component into another. Absorption goes beyond the adsorbent's surface layer. But for today, we'll only discuss adsorption, which again is limited to surface interactions. Now, as you might recall from our earlier filtration video titled Most Penetrating Particle Size, diffusion tends to be the primary filtration capture mechanism for very small particles. Diffusion is influenced by a particle's Brownian motion. And Brownian motion, as you might recall, inhibits a small particle like a molecule from traveling in a straight line. Now, fortunately for us, diffusion makes very small particles more susceptible to capture because it increases the chances that a small particle will come into contact with our filter or our adsorbent. So once these molecules come into contact with our adsorbent, what happens? Well, it turns out that there are two subclasses of adsorption: physisorption and chemisorption. These terms might sound intimidating, but hang in there. Their definition is actually rather straightforward, so in our discussion will quickly come into focus. Physisorption relies on an attractive force between the adsorbent, in our case a filter component or an additive, and the adsorbate, those particles or molecules that we're looking to capture or filter. Once in contact with one another, the adsorbates remain in contact with the adsorbent due to van der Waals forces. Van der Waals forces are relatively weak attractive forces. Nonetheless, they do enable an adsorbent, the filter, to retain particles and actually build up layers of particles onto its surface. Van der Waals forces are more common than you might expect. They're the forces that keep dirt particles stuck to the fibers of your clothes, and they're also the forces that keep cigarette smoke particles stuck to your hair or your skin. Fortunately, these attractive forces are reversible, and adsorbates can be removed from the adsorbent. Physisorption is the mechanism responsible for the capture of solvents and dispersed oil particles and hydrocarbons and silicones. Okay, so that's physisorption in a nutshell. Chemisorption also relies on diffusion and Brownian motion to bring an adsorbate into contact with an adsorbent. However, once these two items are in contact with one another, there's an actual chemical reaction that takes place between the two. This reaction creates a very strong chemical bond between the two, which is typically irreversible. Unlike physisorption, that allows layers of adsorbates to form on an adsorbent, chemisorption reactions take place in a single layer on the adsorbent. In other words, there are a limited number of reaction sites that facilitate chemisorption, and those sites are typically proportional to an adsorbent's surface area. When a porous absorbent, like activated carbon, is used, the adsorbates rarely can penetrate into the depth of the carbon particle, which means that an adsorbent's efficiency is usually highly influenced by its available surface area. Now, this is important, so let me repeat this point. An adsorbent's chemisorption efficiency is highly influenced by its available surface area. In other words, more surface area means more bonding sites. So with these facts in mind, let me ask you, what features would you look for in a chemisorptive filter media to maximize the media's ability to remove an unwanted gas phase contaminant? Well, you might answer this way. I want a material that first and foremost maximizes capture via diffusion. By maximizing a filter's diffusion property, I maximize the filter's ability to capture small particles. Then, I want to maximize the adsorbent surface area. By maximizing the adsorbent surface area, I maximize 1, the area that can be used in a bisorptive capacity, and 2, the area where chemisorptive reactions can occur. By simultaneously increasing particle capture via diffusion and the adsorbent surface area, I maximize the filter's ability to remove unwanted contaminants via adsorptive filtration, or its two subclasses, bisorption and chemisorption. Wow. Now that's a great answer. And I agree. So let's look at how Thermopore's polymesh media has been engineered to deliver the same properties. Thermopore's polymesh absorptive filtration media is comprised of 2 outer scrims that function as a wrapper for the material's internal adsorptive ingredients. In this case, the outer scrim is composed of 2 polyester nonwoven materials. But understand that we have design and manufacturing flexibility to use any number of materials as the outer scrim. Inside the scrim, you'll notice our adsorbent material. In this case, it's an activated carbon. We mentioned before the importance of maintaining active surface area on the adsorbent. And this is really where the polymesh absorptive media shines brightest, through the patented use of a fibrous binder matrix. The polymesh media maximizes available surface area, as can be seen in this SEM image. As we discussed earlier, active area plays a key role in performance. And notice how the use of a fiber binder maximizes the useful area of the adsorbent. Not only that, but the use of a fiber binder enhances diffusion capture by creating a tortuous path that the adsorbates must navigate during their travel through the polymesh matrix. Need even more capacity? No problem. With the polymesh media, adsorbent loadings up to 1,000 grams per square meter can be realized. When you combine the way that polymesh maximizes available surface area with the design and flexibility of various outer scrims, adsorbent weights, and converting options, you get best-in-class performance. So you might ask, what other competitive materials are on the market? Well, let's take a look at 2 alternatives: sludge-coated media and extruded media. Sludge-coated media is essentially a non-woven substrate that's been submerged into a mixture of resin and activated carbon powder. The submerged substrate is then patted and dried in a curing oven. Typically, this material will have little dusting or particle shedding and a low differential pressure drop, which is good. However, as is evident by the picture, the actual carbon content is low. Therefore, the media suffers from poor adsorption efficiency. A second competitive technology is an extruded carbon technology. The extrudate is actually an activated carbon matrix sandwiched between a top and a bottom non-woven outer scrim. The carbon granules are secured in place with an adhesive or a binder. It's a pretty good technology, but as can be seen in this image, the binder oftentimes is covered or occluded, and you should know by now what impact that can have on our performance. Companies requiring best-in-class absorption filtration efficiency select Thermopore's polymesh chemisorptive filtration media time and time again. I hope now you know a little more about why that's the case. Thermopore maintains a diversified portfolio of porous materials that can help you achieve any number of applications involving filtering, wicking, diffusion, and venting. And I hope that this tutorial has provided you with some insight into the types of variables that we'll be able to tweak to satisfy the needs of your next chemisorptive filtration development project. Stay on the lookout for additional videos by signing up for our RSS feed. And as always, if you have any additional questions or if there's some topics that you'd like to see added to the Thermo TV channel, well, give us a call or feel free to drop us a line. For now, I'm Ken Milam saying thanks for watching this installment of Thermo TV. We'll see you next time.